Now let's try to validate the reciprocity using SW4. So this is one of the steps that I've always taken before we actually start to compute the sensitivity kernels. So if the reciprocity is valid, then the calculation of the sensitivity kernels using the scattering integral method is are very likely to be correct, right? So validating reciprocity is like a quite important step, just to make sure that the rest of the kernel calculations will be will be will be correct. Um, so the setup is following the classic paper by Li Zhao back in 2005, right? Um, so it's Li Zhao's paper back from 2005. That's BSSA free shade kernels for imaging regional Earth structure based on three-dimensional reference models. Uh, I'm one of the co-authors, but uh, Li actually did pretty much all the work. So so in his paper, he actually gave some canonical examples for us to actually check the validity of the kernel calculation. So so he did like three examples, right? The first one was a explosive source buried in a half-space model, and then a second example is a double couple source buried in a half-space model, and then the last one he did was for three-dimensional structure models using realistic earthquake sources. Those are kernels, right? For this paper, there was some this kind of a oscillating patterns close to the surface, right? But but that was the first paper, right? That was the first paper. And there, for the next one, published in 2006, which is called. Let me see if I can actually find it. Um, my papers. Right. For this one, those those problems have been eliminated. Right. So we have actually corrected those problems. I myself, after I sort of graduated as a graduate student from VSC, I myself started working on the kernels, and I myself also made some improvements to both the efficiency and the accuracy of the kernels. Um, so now this kind of oscillating pattern is no longer a problem for us. Right? There's no oscillating patterns anymore. But for now, we're not exactly computing the kernels yet, so we are pretty much just using this example to actually validate the reciprocity. Right? So reciprocity is supposed to hold if if the if the numerical calculation is accurate enough. Right? That's like a that's the expression of the reciprocity, mathematical expression of the reciprocity using Green's tensors. So so if you compute the Green's tensor from source which is located at R and record the nine-component Green's tensor at receiver location R, capital R, then it's supposed to equal to the transpose of the Green's tensor computed by using by placing the source placing the impulsive source at receiver location, right? And then record at grid location R. Right? There's a transpose here. But in our calculation, in this in this example, we're not really computing the nine components of the Green's tensor. Instead, we're going to compute the synthetic seismograms. So the synthetic seismograms are basically just a moment tensor convolved with the gradient of the Green's tensor, right? So the gradient of the Green's tensor is actually the strain field. So um, Green's tensor is displacement, right? So if you have a spatial gradient on top, if you take the spatial gradient with respect to the displacement, you're supposed to get the strain. So so basically you're convolving a moment tensor source with a strain field, right? Um, so the geometric setup is more or less like that, right? So you gotta so this is more like a cross-section view. This is the simulation box, right? So source is here, receiver is here, right? And then in my setup, I actually reversed the position of the source and receiver. So source is on this location and receiver is on this location. So source is to the left, receiver is to the right. And then they are buried at 24 kilometer depths. Both source and receiver are buried at 24 kilometer depths below free surface. And then um, uh, the distance between the source and receiver is 32.2 kilometer. If I recall correctly, that's like the setup for right. So the source receiver distance is 32.2 kilometer. Um, and then density is like this. P and S velocity is like this, right? So uh, that's like the structure model and also the geometry. So this source model for the explosive source, there's a time function to it. For the explosive point source, there's a time function which is a Gaussian, and this Gaussian has a frequency has a maximum frequency of about 2 hertz. So this is the Gaussian. It's got like two parameters, A and B, right? So half of B is like the shift of the Gaussian, the time shift of the Gaussian, and then A is like the inverse of the width of the Gaussian. So A equals to 60 and B equals to 0.65, right? Um, so that's the source time function of that point explosive source. Um, so we have to compute the synthetic seismograms at least to like 2 hertz. That's like 0.5 seconds, right? Um, so for this kind of structure model, for this kind of for this particular velocity model, to compute the seismograms accurate to 2 hertz require a grid spacing of 200 meter. Right? So the grid spacing is 200 meters in my in my in my in my in my in my tests, in my checks. Um, anything else? Anything else? So synthetic seismograms is going to look like that, right? So if you put the source here, receiver here, and x direction goes from left to right, then the first swing of the direct arriving P wave is going to be negative, right? Because an explosive source is a kind of it's going to create a P wave that actually goes this direction, goes the negative x direction, goes goes in the negative x direction. So the x component is gonna have a negative amplitude. Initial amplitude of the P wave is gonna be negative, right? But if I switch the location of the source and the receiver, so if I put source here, receiver here, and then x direction still goes from left to right, then the amplitude, the first swing amplitude is supposed to be positive, right? Because the source is here and it's an explosion. So the first motion is supposed to be positive, right? So in my synthetics, it's gonna be the amplitude is gonna be kind of the opposite of the synthetic for the x component. For the x component, the amplitude is gonna be the opposite of the synthetic that's displayed here, right? And we're gonna compute the synthetic seismogram up to like 15 seconds. Right, so we're gonna see three phases, right? The direct arriving P, small p, big P. That's like the surface reflected P, right? So P goes to the free surface, gets reflected, and then gets reflected back to receiver. So that's small p, big P. And then you also have a surface converted, right? So when P hits the surface, it's gonna not just do a reflection, but it's also gonna do a conversion to S, and then gets back to the receiver. That's PS. Right? So here you see some small wiggles here, right? Some small wiggles, but using SW4, and if you take 200 meter grid spacing, you won't be able to see those kind of numerical oscillations. Those are purely just numerical, right? And then the time stepping has to be sort of the time step length. If the time step length is small enough, right, then there's not supposed to be a significant amount of numerical error, right? So that's pretty much the geometric setup, right? And then there's another double couple source. So where's my double couple source? Um, the double couple source has a dip of 45 degrees, a rake of 45 degrees, and then the strike is supposed to be 90 degrees from the x direction. So if x actually points to the north, and if it's a right-hand system with z pointing down, then um, that's the SW4's convention, right? And SW4's coordinate convention is actually consistent with Archie and Richards. Uh, then it means what? It means the focal moment has strike in y direction. That's AWP's y direction. So AWP's y direction, um, that's more like that's equivalent to SW4's x direction, right? Um, so in SW4's coordinate, it's the strike is supposed to be in the x direction. That's in the north, I think. So the strike is supposed to be 0 degrees, and then a dip of 45 degrees, a rake of 45 degrees. So strike, dip, rake, and it is 0, 45, 45, right? That's changing the focal mechanism from an explosive source to a to a to a to a to a double couple to a double couple moment source, right? So that's gonna be the geometric setup, right? Um, so what's gonna be the input? What's gonna be the input to the simulation to SW4, right? What's gonna be the input for these two sources for SW4, right? Let me see if I can get to the directory. So I'm doing the experiment underneath this particular directory on Mount Moran. So it's called a half space, right? So HS abbreviation, half space. And then if I go into this directory, I'm gonna see three directories: FWF for forward wave field. That's all the wave fields, the strand fields basically. And then jobs, that's some scripts and some input files for all the simulations. And then VM, that's the velocity model. That's not just the velocity model, but also for storing all the information that's related to the velocity model. You can sort of see some of those files that I mentioned in previous videos. And then in FWF, I'm supposed to see like a couple directories. So that's the two sources. So 100001 is supposed to be the explosive source, and this is supposed to be the double couple source. And then I've got like a receiver side string green tensors for the three point sources, point impulsive sources, pointing in the SW4X, SW4Y, and SW4Z coordinate directions. So if I assume that X points to the north, so this is the receiver green tensor for a point force, pointing positive force that's pointing to the north, right? And then SW4 uses a Y right-hand system, so X goes north, then Y is supposed to go where? Go east, right? So this is supposed to be east. Point for the point force, pointing positive force pointing to east and located at receiver location, and then this is pointing down at the receiver location, right? The impulsive force. So if we look at one, so that's the directory for storing the simulation results for the explosive source, right? So the main input file is supposed to be this .in file, right? It's quite short. But it pretty much has everything. File IO, that's the path for storing the output files, for storing the data output files. Parallel file system equals to 1 because I'm running on Mountain RAM. Mountain RAM doesn't have a parallel file system, so I set PFS to 1. Verbose 2 print cycle 10, that's like a 10. Every 10 steps, it's gonna write out a a synthetic cytogram. And then the important thing is this are these two lines basically. So that's grid. There's no fancy grid manipulation here because I'm not doing any kind of refinement. So it's just one uniform grid, one uniform finite difference grid with a uniform grid spacing of 200 meter. So the default unit is meter, and then nx equal to 250. That's like a 250 grid points in the x direction, in the north direction. 250 times 200, that's like 50 kilometers. 50 kilometers, right? 50 kilometers. No, it's actually 409, 49.8 kilometers, right? Because 250 grid points, that's like 249 grid spacing, right? Grid spacing, 249 times 200. So, and then in the y direction, it's 150 grid points, and then in the vertical direction, that's 200 points. And then if the velocity model is like uniform, I don't really have to specify an R value or anything. I can just use the block command. So SW4 has multiple ways for specifying the velocity model. So if the velocity model is purely just a uniform structure model, then you can just use one block command with the correct VP and VS, and also density. So the unit is in meters per second for the velocities, and for density it's kilogram per cubic meter, I think. And then time, that's for the length of the synthetic cytogram, 15 seconds. So we're going to do the simulation for like 15 to compute the synthetic wave field for like 15 seconds. And then I have a source. That's the source command. That's the location. That's the coordinate of the source in x, y, and z. So in x direction it's 8,800 meter. In y direction it's like a 15.9, 14.9, 14,900 meter. And then in the z direction it's 24 kilometer, right? 24 kilometer. And then it's an explosive source, so I have to specify the moment tensors, right? So mxx, myy, and mzz, 1 to the 10 to the 15th power. And then the type is a Gaussian int. Why it's a Gaussian int? It's an integral of a Gaussian, right? It's an integral of a Gaussian. So SW4 is different from AWP. AWP actually solves the velocity stress formula, but SW4 actually solves the displacement, solves the elastic wave equation expressed in the displacement form, right? So if I want to compute the displacement field, the strain field is the gradient of the displacement field. So if I want to compute the displacement field, the source time function is supposed to be the source time function is supposed to be the source time function for the displacement instead of the instead of the moment rate function, right? So that's one of the differences between SW4 and AWP. So in AWP, because it solves the velocity stress formula, so you specify the source time function in terms of the moment rate, right? But here it's actually solving the displacement equation, so you have to specify the source time function in terms of the moment as a function of time, not moment rate as a function of time. So and then it provides this Gaussian int, this particular time function, as it's built as one of those built-in source time function. And then I have a shift of 1.0. That's one of the differences between this experiment and the one that's documented in Li Zhao's paper. Because in Li Zhao's paper he was using a shift that's like 0.35 seconds or something, right? But here I'm actually using a shift that's like 1 second. So it's slightly delayed. Can't find the number, but doesn't really matter too much. Right? T0, which means I'm shifting the Gaussian pulse by like 1 second from 0, right? So the peak of the Gaussian is going to be located not at 0 but at 1, right? And then freq, that's the frequency. How do I actually get the frequency? Because in the equation that's given in Li Zhao's paper, A equals to 60, right? A equals to 60. And then in the user manual for AWP, SW4, um, Gaussian and Gaussian int, it's actually using, so a Gaussian looks like that, right? That's the expression for the Gaussian. So if I compare them, A actually equals to omega square. The omega is frequency in terms of hertz. It's not angular frequency. It's just the frequency in terms of hertz. Right. So 60 equals to omega square. So all I have to do is to take the square root of 60. That's 7 point something in order to actually get the right frequency. Right. So f freak here is equivalent to omega in that equation. That's the omega here, right? That's the omega here. So that's the square root of 60. So that's gonna be my source specification, the location and the time function. It's a point force, right? It's a point source, and then with a explosive moment, isotropic moment. And um, at the receiver is supposed to be like a 32.2 kilometer away, right? So x is, so this line is for receiver location. So x is gonna be at 41 kilometer, right? So 41 subtract 8.8, that's like a 32.2, right? And then y is at the same coordinate, and z at the same coordinate, right? So the source receiver distance is 32.2 kilometers in the x direction, right? So, and then y and z are kind of identical, and then the output file is going to be in.rc01, and then the important thing is here, variables. Variables equals to velocity. So I can specify multiple kinds of uh, outputs, right? So by default, it's going to compute displacement, right? But if I specify variables equal to velocity, then it's going to take a derivative of the displacement at the receiver location. I mean, a temporal derivative to get the velocity, right? A temporal derivative of the displacement to give me the velocity. And SEW equals to 0 means I don't want to really rotate the synthetic subsequence to the north, south, east, west directions. And then I'm not using the SEC format. I'm using the USGS format. Write every for every time step, I'm gonna write a one output to the synthetic subsequence file. And that's the explosive source. And then I also got a double couple source, right? It's pretty much similar. Everything is similar. The only thing that's different is the moment tensor here. So by default, all the moment tensor components are by default are zeros, right? So these two components don't have to be specified actually. So if it's 0, you don't have to specify it. You only need to specify those moment tensor that's non-zero. So mxx, that's like equal to this thing, 10 to the 15th power, and then mzz equals to this thing, and then myz equals to this thing. So um, so you can compute the moment tensor using the form. You can convert the moment tensor. You can compute the moment tensor from strike dependent rake angles by using those equations in Archie Richards' book. That's kind of a very easy calculation. So there are existing formulas for doing that. So that's not really a big problem. The only thing that I have to pay attention to is to make sure that the coordinates. So the formulas in Archie and Richards' book is for converting strike dependent rake angles to moment tensor in a coordinate system that's with x pointing to the north, y pointing to the east, and z pointing down. So that's a coordinate system that's consistent with SW4. But if I'm using a different coordinate system, then I have to do the rotation of the moment tensor. I have to be slightly more careful about how to do the rotation. of the moment tensor. It's because it's a two-dimensional tensor. It's a matrix. How to rotate that tensor matrix is kind of has to be sort of implemented. Um, I have that thing implemented back in the AW in the inversion code for based upon AWP. So later on I'll just copy those codes over. I think it's not really that difficult. It's just um, multiplying with the rotational matrix and its transpose in some kind of order. So that's not too difficult. So that's pretty much just the input specifications for the two sources, right? So let me still go back to the directory for storing the explosive source, right? So after the calculation is done, I'm supposed to see this particular file. That's the synthetic Sandworm file. So if I do a head, then it's gonna tell me uh, some information, right? Some information. Those latitude and longitudes are actually just some built-in values, some kind of a hardwired values, because I'm not specifying the latitude or longitude of the source. I'm just specifying the meters. But and then it's gonna give me 4 different columns. The first column is zero, is time, and then the next column is x velocity, y velocity, and then z velocity in terms of meter per second. The time step interval was computed by SW4 automatically to satisfy the CFL condition to make sure the simulation is actually stable. So we can actually sort of compute the dt, the time sampling interval, based upon these kind of outputs. And it's supposed to actually run the simulation up to like 15 seconds. Right, that's about 15 seconds. And then that's the velocities. So later on I'm gonna sort of plot those velocities. Right. And then the same is true for the other directory. For the double couple source, there's this particular file. Right. That's for storing the synthetic velocity of this particular double couple source. And the screen dump are stored in those Slurm output file. That's the output file created by the job management system. So this file is also quite useful. It prints out lots of quite useful information. For example, it's telling you the total number of grid points, the boundaries, and of each of the process. So I'm running this particular job using 160 cores. So the job script looks like that. So that's my job script. It's a very short job script. So I'm running on 10 nodes, and each node I'm using 16 cores. So it's a very small job, and 30 minutes long. But that's so the entire simulation takes like a few minutes, 1 or 2 minutes actually. And then I'm running SW4 with this as the command line input, with this file as the command line input. And then it's supposed to create the synthetic Sandworm file. And then these WF files are actually strand fields that's going to be used for computing the kernels later on. Right. So for the forward simulation, the input files are quite straightforward. There's not a lot of tricky stuff involving it. Right. So I have a MATLAB script here. Right, I have a MATLAB script here. So this read USGS function is provided by SW4. So it's a MATLAB script for me to actually read these kind of output files created by SW4, synthetic waveform. The reason I'm using read USGS is because here I'm using USGS format equals to 1. So the output file is going to be written into a text file that's called USGS format by SW4. So here I'm using this read USGS script to read that file in. The output is going to be TUVW. So the first column No, the first column. The second column is displacement, the velocity in the x direction, velocity in the y direction, and then velocity in the z direction. So dt is just the t2 subtract t1, and then from that I can compute some Nyquist frequency and construct a Butterworth filter, low-pass filter to filter the synthetic seismograms somehow. It's the synthetic seismogram actually looks really clean. I don't really have to actually filter it in any way. But the reason that I'm filtering it is because there's a filter that's built into the receiver Green's tensor, the RGTs, receiver Green tensors. So when I actually compute the RGTs, there's a filter built into it. Right? So when I actually validate the reciprocity, uh, that filter, that low-pass filter used for computing the RGTs has to be convolved with the forward seismograms. The synthetic seismogram computed from the source, right? And that convolution is equivalent to doing this kind of filtering. So that's why I'm doing this kind of filtering here. Uh, and then I'll explain this section of the script later on. But here it's making the plots. So US2R, that's from source to receiver. That's the velocity in the x direction, and then VS2R, that's the y velocity from source to receiver, and then WS2R, that's the z velocity from source to receiver. Right. Those three curves are plotted in black. So if you want to look at the seismograms, the black curve, which you can hardly see here, uh, is actually the synthetic seismogram computed from the source to receiver. You can see the black curve on the y component. So this is the x component, this is the x component, this is z component, and then this is the y component. Right. Um, okay, so that's for the forward simulation from the source to receiver. Right. And now let's look at the simulation, the Green's tensor simulation from the receiver to the source. Right. So I'm placing three pointing positive forces at the receiver location. This directory is for the simulation with the pointing positive force that's pointing to the x direction and located at the receiver location. And then this directory is for a force that's pointing to the y direction and located at receiver. And then this one is for the pointing force pointing to the z direction and located at the receiver location. So let's just look at what's actually inside of this directory. Right? It's kind of similar to the simulation that's for the explosive source. The only thing, but the important thing is to look at the input, right? Let's look at the input. So this part of these lines are kind of similar. There's not much a difference. The tricky part is in terms of specifying the source and also the pre-filter and also the receiver. Also the receiver. So what's going to be the source, right? What's going to be the source? The source is going to be a 0.4 source, right? So the source is going to be located at the receiver location. So the coordinates are going to be identical to the receiver coordinates for those source directories, right? For example, if you look into 100001, the receiver coordinate is 41,000. 41,000, right? Y is 14900, 1490. These 24,000, right? So the source location is the same as the receiver location, and then the source is going to be a 0.4 source with a scalar amplitude that's like 10 to the 15th power. And then because this is in dot x, that's the 0.4 in the x direction, so fx equals to 1. And then fy and fz equals to 0. And then what's going to be the source type, right? When I was when I was using AWP, what I did is that I use a source time function that's generated by myself. So how I actually generate the source time function, right? In AWP, I I basically just use a Butterworth filter that's created in MATLAB, and then to filter a impulse with the first data point 1, and then all the rest of the data points 0, right? And that's gonna give me the time history um, of a low-pass filter, a Butterworth low-pass filter, right? So basically, I just use those lines to create the filter, and then I use the filter to filter a impulse to create the time history for the source time function. That's what I tried at the beginning because SW4 does provide this kind of capability. It's called a D file, and then D file has to be with a certain kind of a format. Um, the format of this file is quite straightforward. It's not really that difficult. Um, so discrete time function. Right? The first line of the file is 3 numbers. T0, that's the starting time. Delta t, that's like the sampling interval of the of the source time function. It doesn't have to be identical to the simulation time step. The simulation time step is computed from the velocities, but this time step is just the time step for sampling the source time function, and then the total number of data points. That's the first row, and then for all the rest of the rows are just recording the amplitudes of the source time function at all those different time sampling points. That's a quite a straightforward format. And then when SW4 require a certain amplitude of the source time function at a certain time, that may not be exactly the time that's provided in the D file, then SW4 is supposed to do some kind of interpolation or B-spline interpolation, right? But the problem is that I couldn't get this thing to work, right? It doesn't really matter. I tried many times trying to sort of to give it the different kinds of format, give the numbers in different kinds of format, and so on and so forth. Uh, but it's not working. So starting time -1 second, sampling interval 0.01 second. I've got this many data points, and then it's just the amplitude, the time history, right? The thing is that it's I couldn't get it to work. Right? The synthetic substituent computed by using this thing looks like it's using a source time function um, that's like completely random. It's not really. Maybe the interpolation. I'm not using the interpolation. I'm not sort of specifying the input format correctly, but the input format looks quite straightforward. Or maybe those numbers. I tried a different kind of formats for the numbers, right? Maybe it's not taking the kind of scientific format. I tried using just the floating points. Uh, but I tried different kinds of formats, but it just doesn't work. But fortunately, it provides SW4 provides the capability for computing the wave fields using a direct force, a direct delta source, basically direct delta source time function, right? And then if you want to sort of use the direct delta source function, the delta function as a source time function, uh, we have to filter it. The user has to specify a pre-filter. The pre-filter is something that's provided by SW4, and it's a Butterworth filter that's kind of used quite commonly. So it's got a let me see. Hmm. Pre-filter, right? Basically, I meant pre-filter. You can specify the corner frequencies. If it's a bandpass, then FC1, FC2 are both useful. But if it's a low pass, then only FC2 is useful. You can specify FC1, but it's not going to be used. So all the all of the inputs has to be so in hertz. So the corner frequency is in hertz. So FC2 equals to 2 hertz. That's the corner. And then by default, it's going to be a Butterworth filter. It doesn't really provide multiple choices, so it's going to be a Butterworth filter. And then, but you can specify the order. So here I'm specifying a 6th order, a Butterworth filter, order equals to 6. Right? So this is actually a very high order Butterworth filter. Usually, in practice, you can just use like a fourth order is like used more widely. Right? So if the cutoff is like sharper, so if the order is higher, then the cutoff is sharper, so it has a more rapid roll-off. Right? But if the order is lower, then it has a smoother roll-off. Right? So here order equal to 6, so it means it's quite a sharp roll-off. And then it gives you the choice of passes equals to 1 or 2. Right? So it's saying that the filter is either forwards in time, passes equals to 1, so that's going to be a causal filter, right? It's a causal filter, but it's going to introduce some kind of a phase shift. But for Butterworth filter, it's sort of a minimal phase, I think. So the phase shift is kind of a minimal for that particular order and for that particular kind of a pass band, right? Another choice is to use passes equals to 2. So it means that it's going to do a forward filter, and then it's going to do a backward filter, which means that it's going to reverse the time of the synthetic wave filter and then do another forward filter, and then reverse the time again. Right? So that's equivalent to that. How it's implemented depends upon how the code is written, but passes equals to 2 is going to give you a 0 phase shift. So it doesn't introduce any kind of a phase. The filter doesn't introduce any kind of phase, but the filter is going to be acausal. It's a acausal filter. So here I'm just using a phase passes equals to 1. So it's a causal filter, but it's going to the filter itself is going to introduce some kind of delay. It's okay, but because when we compute the kernels, we can account for this delay, right? That can be accounted for. And then the type is going to be a low pass, so it's only FC2 has to be specified, right? So combining these two commands, basically use a direct type of source time function and then use a pre-filter. It's going to give me the same kind of effect as this one, as using a using a source time function created by myself. Right? It's gonna produce an equivalent effect, and this actually works. This kind of specification actually works. The only thing that I have to pay attention to is T0. Right? T0 is actually the location of the pulse. So you cannot specify T0 equal to 0. You cannot do that. Because if you specify T0 equal to 0, then the output is just going to be exactly the same as using a filter without any kind of using a impulse without a filter, without any kind of pre-filter. Right? Why do I actually specify this number? Right? This number is actually 3 time steps. So that's what I have found using through experimentation. So if the pulse is located at 3 time steps, then the effect of the pre-filter is going to be correct, right? So if you shift the T0 to a time that's larger than 3 time steps, then it's also going to work, but the waveform are not going to be different. The waveforms are going to be identical, except that the delay time is going to be sort of dependent upon this thing. But if T0 is smaller than these 3 time steps, then the shape of the waveform are not going to be what I wanted. Right? The shape of the waveform are going to be identical to an impulse without a pre-filter, actually. Right? So 3 time steps is like the minimal amount of shift of the pulse. But it's still okay, right? Have some time shift is still okay because when we compute the kernel, we can account for the time shift when we actually read the Green's functions. So that's the source source side of the things. And then for the receiver side, I have to record the strain. I have to record the strains. So variables equal to strains. This is indeed a strains, right? So it's a symmetrical component. It's a symmetric thing, right? Symmetric strain tensor, right? So it's gonna store all the 6 independent components of the strain. Right. And then if you look into the .y directory, then the only thing that's gonna be different is the only thing that's going to be different is actually in terms of the force. So now fx equals to 0 and fy equals to 1, right? Fz is still equal to 0. And then if you look into the z directory, so fz equals to 1, and then fx and fy are both zeros, right? And then if I sort of look at the output file are going to be stored inside of this particular file, right? Because I was specifying the strain, so it's gonna give us like 7 columns. First column is still time, but the rest of the 6 columns are gonna be the strain components, right? X X Y Y Z Z, and then X Y X Z, and then Y Z, right? That's the strain components. Y X is gonna be the same as X Y, and then Z X is gonna be the same as X Z, and ZY is gonna be the same as Y Z. And then and then all I have to do is to read those files, basically. Right here, read USGS again is for reading those files. The file name has been changed to reflect the fact that it's going from the receiver to the source. Right here, the calculation gives me just so this output file can be the output file name can be actually specified. So it doesn't have to be the output file name is what is 1001. So what I'm supposed to do is what I should have done is to actually just specify this as the output file name here. So later on I don't have to sort of manually rename all the output files. And so in the other directory, I'm supposed to have this file, right? And then this file is renamed to this file, right? So I'm reading that. And then for Z directory, I have pretty much the same, all those things, right? And then those are strain fields, right? Strain fields. So in order to actually get the velocity, what I have to do is to actually to multiply with the moment tensor and then convolve with the source time function of the source, right? So when I actually read the synthetic seismograms from the source, I have to do this kind of filtering, which is basically convolving the source time function of the Green's functions, Green's tensors, right? To do those filtering. Here, after I finish the reading, those Green's tensors which are filtered already, which has this filter built in, but don't have those don't have the Gaussian, the shifted Gaussian as the source time. So shifted Gaussian is built into those synthetic seismograms from the source, right? But those Green's functions don't have those source time function in it. So I have to sort of manually create that source time function, right? So FCN plot is one of those functions provided by SW4, right? So I can create Gaussian with the correct frequency, a time duration, a shift amount, and then if I want to make a plot, I can specify the kind of plots, and then dt is the time sampling interval of of the syntactic hardware, right? And then that's gonna give me the Gaussian that's used as the source time function for the forward syntactics. Right. So after I finished reading those syntactics from the from the Green's tensors, I have to sort of multiply with the moment tensors, right? With the moment tensors, there's a 2 here, right? 2 here. There's a 2. There's a 2 here. The reason for those cross terms x, y, x, z, and y, z, you have to multiply 2 because you have to account for the moment tensor. That's because you have mxy. This is mxy, right? But you also have myx, right? But myx times uyx is equal to mxy times uxy, and then you account for that the factor of 2 here, right? And then I have to do this kind of convolution with the Green's with the source time function. That's for the forward simulation. That's the convolution here. The convolution has to multiply delta t because otherwise it's not going to have the correct amplitude. That's a MATLAB convolution function, right? So for MATLAB convolution function, you have to multiply with the sampling interval in order to actually get the correct amplitude. Otherwise, there's going to be something weird about the amplitudes. Right. But this line is just for getting the shift right, right? Because the Green's function was shifted by 3 time steps here, right? So that's like shifted to the back, delayed for like this much, right? So so I have to sort of advance it. So I have to advance it by this much. So how do I actually advance it by this much? I just do this kind of a subindex thing, and that looks like sufficient, right? So and then if I do this, that's for the 3 different components, right? Yeah, that's for the 3 different components. Up to here. Okay, so oh no, I think okay. So this is the reading the strand fields that's computed directly by SW4 as one of those outputs, right? This section of the code, and then this section of the code, and then this section of the code for the x, y, and z directions, right? And then for each of the sections, I still have this code. So maybe I should just add a comment. So this part is for the x component, this part is for the y component, and then this part is for the z component, right? And then for each of the components, I have 2 sections of the codes. This is just using the output file, synthetic arithmetic file created by SW4. But this part of the code is using a output file that's created by my own RGT to sing function. So I wrote a function for converting the receiver Green's tensors to synthetic sonograms. Right? Those are the outputs. Right? So those outputs were created by using from SW4, but those things, RWF underscore X out, RWF underscore Y out, and RWF underscore Z out, those files were actually created by using a RWF function. So if I look into the bin directory, there's a RWF here. That's for just reading the strand fields from the receiver side, or reading wave fields, basically, just reading wave fields. That's the binary, and then it's gonna create outputs that's like 6 columns. That's the strand fields. The only thing that the strand fields, it's gonna what this function is gonna do, what this code is gonna do is that it's gonna sort of extract the strand volumes at the location of the source. of the forward source, basically. Right. So strain has like 6 components, so it's gonna extract the strain fields from the strain volume. So it's gonna extract the strain time history at the location of the forward source from the strain volume. Right. Um, so if I look at the code rwf.cpp, that's really straightforward. So just to specify the name of the strain field file, um, and then the number of components, that's 6. The number of time steps after decimation, that's 471 for this particular example. Total number of grid points, and the grid ID that I want to extract, right? And then it's going to write out the strain history at this particular location, right? That's like 6 components for every time step, right? And those files rwf underscore x, rwf underscore y, and rwf underscore z, right? Um, so what's going to be the difference, right? There's not supposed to be any difference. They are supposed to be those files are supposed to have exactly the same kind of information or same kind of numbers as those files, right? The only thing that's different is for those cross terms. Those cross terms, right? So if I look at the U component, so those cross terms created by using those this read wave field file is going to be twice as much as the cross terms that's read from the output file or synthetic seismogram file created by SW4. Right. So here I divide by 2 here, and then multiply by 2 here. Right. This multiply by 2 is actually identical to this thing to this part of the code, but divided by 2 and then multiply by 2, this is like cancels out. So if I'm using my own file, all I have to do is to actually multiply the moment tensor with the output of the column of the file, right? I don't have to do a multiply 2 if I cancels out this. So what's actually stored in those output files are actually twice as much, 2 times those cross terms of the strain fields. Right? It's not exactly strain fields, it's actually 2 times the cross terms of the strain fields. Right. So if I run this thing, it's gonna give me this kind of so those files are plotted in 2 different kinds of colors, right? So UR to S, that's the receiver side of synthetic seismogram using the strain outputs of SW4, and then U1 R2S, that's using my own. I have to pay attention to the first point. So my own file doesn't actually store the first point because it's always 0, right? But the file created by SW4 actually includes the first 0 in its output. So in order to do a fair comparison, I have to sort of add 1 0 to this particular vector, right? And then I'm plotting them, right? So that's plotted in blue, and then that's plotted in red, right? So these two are supposed to be identical. If my strain calculation is actually identical to the strain calculation of SW4, then these two things are supposed to be identical. So I'm not supposed to see any blue curves. So red curve is supposed to be on top of the blue curve, right? And then black curve is from the forward simulation, from the source to receiver. Both red and blue curves are from the calculation of using the Green's tensors. So you don't see any blue curves here, which means my strain calculation is kind of identical to the strain calculation of um, the of SW4, but you do see differences between the red and the black. That's the forward simulation, that's in black, and the synthetics from the receiver Green's tensor is in red, right? Some small differences for here. some slightly bigger differences for this P to S conversion, right? Some slight differences for this P to P conversion here. Slight differences for P to P conversion here. Right? But for this Y component, this is for X component, right? This is for Z component. For the Y component, the difference is kind of a bigger visually, right? But if you look at the scale of the amplitude, that's like 2 times 10 to the minus 7. But here it's like 2 to the minus 2 times 10 to the minus 5, 4 times 10 to the minus 5. So this other one is like 100 times smaller than these two cybernograms in terms of amplitudes, right? So if you plot them on the same kind of color scale, same kind of vertical scale, Y scale, then the difference here is kind of minimal. You can't even see them, right? But there's still some kind of differences here, right? I have no idea why, but it's probably related to how SW4 is implemented, right? The numerical algorithm of SW4. So the numerical algorithm of SW4 itself may have something that actually violates the physical law of reciprocity, right? It doesn't look like a numerical noise. The frequency of the waveforms seems to be correct, right? It's not like a numerical noise. So there might be some numerical implementation that actually violates reciprocity at some location of the code. Maybe it's associated with free surface boundary conditions, or maybe it's associated with absorbing boundary conditions. So it's using some kind of the thing that's called a supergrid as absorbing boundary conditions. So the default value is going to be 30 grid points. Maybe those things were associated with the implementation of those supergrids, right? And this is for the explosive source, right? It's for the explosive source. And then if I do the double couple source, so all I have to do is to actually change the file name from 1 to 2. That's the double couple source, right? And then I have to change the moment tensor. Comment here, uncomment here, and then run it again. Right? That's for the double couple source. So you can sort of see some differences here, right? It's like a visible, right? Some visible differences. That's associated with the free surface phase, right? That's a phase that's associated with the free surface. So there might be something that violates reciprocity at the location of the free surface, right? But in general, the discrepancy is kind of very small, right? So it's not going to affect the accuracy of the kernel calculation by too much, right? So for inversion purposes, these kind of differences are kind of negligible. It's not really that big a deal, right? And then the last thing for this video is about a code for computing the. So here I'm actually computing the synthetic seismograms from receiver green tensors inside of MATLAB script, right? Using MATLAB script. But I have a function for doing that. Have a binary for doing that. It's called R2sing. Now R2S basically. R means RGT. 2 means 2. To S means synthetic. So from RGT receive a green tensor to synthetic seismograms. So that's a function. That's a binary for doing that calculation. So it's got lots of command line inputs. Info path. That's the path for storing the velocity model and its related information. Wave field path. That's the directory for storing the simulation, the stream volumes. Those files basically. Right. They are actually stored in different directories. And then XYZ, that's the source location. Wave field path, right? And then moment tensor. For now, it only takes moment tensor, the six component moment tensor, and then the output file name. So it's got like 13 command line inputs. And then in order to run it, That's how it's run, right? So the synthetic subdomain is going to be stored under the current directory, and then it's going to be called dump. Um, that's the directory for storing all the information files related to the velocity model and the grid. The grid spacing in terms of the meters, the source location in terms of meters. Right, for now, it's not taking latitude, longitude, and so on. And then the directory for storing the stream field, the stream volumes, and then the moment tensor in terms of xx, yy, zz, xy, xz, and yz, and then the output directory. So the output is going to be just one column that's going to store the synthetic sonograms. Right, so it's R to syn, R to S, it's R to S. R to S for computing synthetic seismograms, synthetic velocity seismograms from receiver Green's tensors. Right, so if I run it, let me just give it one run to make sure that it still works. I didn't make any kind of mistakes. So it's gonna, based upon the information about the grid, it's gonna try to actually identify which partition of the grid the source is actually located in, and then it's gonna identify the correct file. Then it's gonna try to identify the correct file, which file it's actually it's supposed to actually it's supposed to read. Right, all those files, all those stream volumes are associated with each of the different partitions. That's based upon the number of processors we're actually using for running this particular simulation. So for that particular source, for this particular source location, it's actually located in the partition that's WF002 and 004. It's supposed to be this file, right, if the calculation is correct. And then it's gonna go into this particular simulation directory and then read that particular file, and then extract the stream fields and then multiply it with or contract it with the moment tensor and then write it out into this particular output file. So that's how to run R to S.